Hello everyone, I welcome you all to this 12th lecture of this course, that is on nanomaterials for cancer therapy. So in this lecture we are going to learn the background of cancer treatments and what are the drawbacks of chemotherapy and what is the advantages of nanotechnology, and also we are going to learn what is passive targeting and active targeting, and also what are the various nanomaterials available for cancer therapy, and we are also going to learn what is theranostic nanoparticle. So according to American Cancer Society, so the lung cancer is the most common cancer in male, and breast cancer is the second most common cancer in the female. So let us see this background of cancer treatments. So 19th century is the birth of oncology, and 1915 scientists at Tokyo University, so they induced cancer in the lab animals for the first time, and these are the various current treatments, okay. So that include surgery, radiation therapy, chemotherapy, hormone therapy, and also targeted therapy. So let us see what are the drawbacks of chemotherapy. So in cancer chemotherapy, so the anti-cancer drugs damage both the cancer cell as well as the normal cells. So thus we need a drug delivery strategy that can selectively kill only the cancer cells and protect the healthy cells. So let us see some of the advantages of nanotechnology. So nanotechnology may help in increasing the solubility and bioavailability of the drugs. That means the most of the anti-cancer drugs are hydrophobic in nature. So by using this nano carrier, we can encapsulate this hydrophobic anti-cancer drug into the nano carrier, and it will also increase the bioavailability of the drugs, okay. And also we can explore the new dosage forms and drug administration routes. For example, we can make the nano formulation which could be given in a different kind of routes. The simple example is we can make a inhalable nanoparticles, and these inhalable nanoparticles can be useful for lung cancer therapy. So these nanoparticles can be inhaled and it can directly go to the lung and it can release the anti-cancer drug, and which will be having like a targeting and enhanced efficiency for lung cancer. Let us see the another advantage is the nanoparticles with diameter less than 200 nanometer. These are not screened out by the circulation by liver and spleen. So if you are making a nanoparticle between 70 to 200 nanometer, it can escape from the liver and spleen, and it can stay in your body for more time, and it can release the drug slowly. And again we can target these nanoparticles specifically to the cancer cell. So that is another advantage of this use of nanomaterials. So let us see some of the other advantages of nanotechnology based drug delivery system. So it provides multi-functionality. That means we can target the nanocarrier, and also along with the nanocarrier we can also add some fluorescent tags, so which can easily monitor in vivo as well as in vitro conditions. And these nanocarriers will improve the therapeutic index, and also it will lower the toxic side effects, okay. And we can deliver multiple drugs directly to the tumor site. So when compared to the traditional method, here in this nanocarrier we can add 1 or 2 drugs in the same nanocarrier. That means it can deliver multiple drugs at the tumor site. And we can also go for nucleic acid delivery or siRNA delivery for cancer therapy, and also it enables the non-drug therapies, okay. Without drug, like for example photothermal or photodynamic therapy also possible using these nanomaterials. So let us see how this nanotechnology improving the cancer treatment. So this is a traditional treatment and this is a nanotechnology treatment. So in the traditional treatment you can see here the drugs, it look like a bomb. So this will go and blast all your cancer cells as well as the healthy cells. So here both the cancer cells as well as the healthy cells both get the drugs and both will die, okay. So that is the major drawback of your traditional cancer therapy. It will kill the healthy cells as well as the cancer cells, okay. But in case of nanotechnology, so these nanoparticles specifically go and bind only to the cancer cells, and it will kill only the cancer cells, and the healthy cells are unaffected. So it is highly specific and targeted, and it is protecting the healthy cells and it is killing only the cancer cells. And these nanoparticles can be targeted to the tumor cells by passive targeting and active targeting. So let us see what is passive targeting. It is based on the retention effect of particle of certain hydrodynamic size in cancerous tissue. So the cancerous tissue or tumor location, it will be having a leaky blood vessels, and it will also have enhanced retention and permeability, that is called as EPR effect. So due to that the nanoparticle will go and bind only to the tumor location, okay. That is called as passive targeting. And in active targeting, you have to add some kind of antibody or peptides which can specifically go and bind only to the cancer cell. The simple example is, if you want to send a letter to Prime Minister of India, you can just write Prime Minister of India, New Delhi. So that letter will automatically reach to the Prime Minister office. So that is called as passive targeting. But if you want to send a letter to your friends or relatives, you have to write the complete address including street name as well as the pin code, everything. So that is called as active targeting. So in passive targeting, you are making a nanoparticle of size between 70 to 200 nanometer. So it will automatically go to the tumor location and bind. Okay. But in case of active targeting, you have to add specific antibodies or peptides which can go and specifically bind only to the cancer cells. So let us see in detail. So the tumor cells need blood to grow larger than 2 mm in size, and the tumor cells will be having damaged blood vessels like leaky blood vessels. Okay. So the tumorous tissue suffer of enhanced permeability and retention, that is called as EPR effect. So we can take advantage of this EPR effect, and this nanoparticles injected into the blood, so it will go to the only tumor tissue region. Okay. So here you can see here, this is a normal tissue region, there is no damage of blood vessels, there is no leaky blood vessels, but in this tumor tissue region you are having leaky vasculature. So which will allow the nanoparticles to accumulate in the tumor location, and it will release the drug and it can kill the tumor cells. So this is called as passive targeting. So next one is active targeting. So in this active targeting, to this nanoparticle you have to add specific antibody and which will go and bind to the cancer cell, and along with this we can also add the imaging agent so that we can easily monitor the nanoparticles, where it is going and binding, how it is releasing the drug, everything we can be easily monitored using fluorescence signal. So here the another advantage of nanotechnology based drug delivery system is, so these drug loaded nanoparticles, it can release the higher dose of drug for prolonged period of time, and which will completely inhibit the growth of cells. And again, mostly the chemotherapy getting failure due to development of resistance to the multiple anti-cancer drugs. Okay. So that is the major reason most of the cancer therapy, chemotherapy get failure, because the cancer cells get resistant to the various anti-cancer drugs. Okay. So in most cases the resistance develops when the cancer cell begin to express a protein known as P-glycoprotein. So this P-glycoprotein, it is capable of pumping anti-cancer drugs out of a cell as quickly as they cross through the cell's outer membrane. So most of the cells, the P-glycoprotein pump will be active. Okay. So when you give the anti-cancer drug, it will immediately pump out your anti-cancer drug. So when you use the nanoparticles, so it will be able to get the anti-cancer drugs into cells without triggering the P-glycoprotein pump. So when you use the nanocarriers, it will escape from this P-glycoprotein pump and it can enter the cell and it can release the anti-cancer drug. So let us see the another technology called stealth technology. Okay. So when you use the EPR effect, the main problem is your immune system. So the immune system will come and attack your nanoparticle. So how to protect your nanoparticle from the immune response? So we have to add a polymer, that is polyethylene glycol. Okay. So that will protect your nanoparticle from the immune cells, and that technology is called as stealth technology. Why we are using PEG, polyethylene glycol? Because it is FDA approved and it is water soluble, and it do not have any immune response or low immune response, and it is highly biocompatible. So by using this PEG, we can protect our nanoparticle from the immune cells. So here you can see the example. So this one is uncoated gold nanoparticle, it is entering the phagocyte, that is your immune cells, and when you use the polyethylene glycol coated gold nanoparticle, and it is the same similar size, but it is escaping from the immune system. You can see here there is no black color dots, that means, so here there is no gold nanoparticle. So when you coat the gold nanoparticle with polyethylene glycol, it is escaping from the immune system, but uncoated gold nanoparticle, it will be taken up by the phagocyte cell, that is the immune cells. So let us see the advantages of pegylation, that means addition of polyethylene glycol group. So when you add the polyethylene glycol group to the nanomaterial, it will increase the size to reduce the kidney filtration, and also it will increase in solubility due to the PEG hydrophilicity, and also it will decrease the accessibility of proteolytic enzymes and antibodies. So it is protecting your nanomaterial from the immune system, as well as it is reducing the infiltration from the kidney. So when you make the nanoparticles or nano drugs, so it should induce apoptosis. Okay, that means programmed cell death. So if your nanomaterial is inducing apoptosis, that is good for your cancer therapy. You can use it for cancer therapy applications. So here you can see the example. Cellular nanoparticle is inducing apoptotic pathway when you use the low concentration of cellular nanoparticle, and this is your control cells. It is untreated cells, and when you treat with the cellular nanoparticle, you can see here it became a round cell. That means these are apoptotic cells. Okay. So when you have the metal based nanomaterial and you can add carbon dots, that is the fluorescent nanoparticles. So in the previous lecture I told you what is carbon dots. Okay. So this fluorescent nanoparticle can be attached to this metal based nanomaterial, silver and zinc oxide nanoparticles. Okay. So when you add this carbon dots to this AgZNO, it will be having both the fluorescence property as well as it will be also having the anti-cancer property. So we can easily monitor the cellular uptake by the fluorescent carbon dots, and it will also induce the apoptosis. So let us see here. So this is a breast cancer cells and this is a lung cancer cells. So these are treated with carbon dots coated metal nanocomposites. Okay. So when you add to these cells, and here you can see here only carbon dots, it is not cytotoxic, the cells are healthy. Okay, there is no cell death, and when you add the increasing concentration of this carbon dots coated nanoparticles, metal nanocomposites, it is inducing cell death. So the cells have become rounded. You can see here the cells become rounded. So the advantage is, so this metal nanocomposites is inducing cell death, and this fluorescent nanoparticle could be useful for monitoring the cell death. Okay. So that is the advantage of having this kind of nanocomposites. So it is having multiple function. We can use it for imaging application, at the same time it is also inducing the apoptosis. And we can also use functionalized inox nanoparticle as a targeted carrier for drugs. So here you can see the example. So in the one of my previous lecture I explained what is RGD, that is arginine, glycine and aspartate. Okay. So these amino acids can be attached to this nanoparticle. So when you have this 3 amino acid peptide, so that will enhance the cell attachment. Okay. You can see the difference. Without RGD peptide the cell attachment is less, and with RGD peptide the cell attachment is more, and it is giving more signal. So let us see how we can eradicate cancer cells by thermal ablation using nanoshells. So this nanoshells have metallic outer layer and silica core, and selectively attract to cancer cells either through a phenomenon called EPR effect, or we can also add some kind of antibody which can specifically go and bind to the cancer cell. So these nanoshells are heated with an external energy source and killing the cancer cells. So this nanoshells, it is having metallic outer layer. Okay. So it is having metallic outer layer and silica as a core, and these nanoshells can be targeted to the cancer cells, and when we apply the light it will generate heat. So that heat will kill the cancer cells, that is called as thermal ablation of cancer cells by nanoshells. So let us see how these nanoshells are killing the cancer cells. So the nanoshells, when you apply this infrared light, so it is generating heat and it is destroying the cancer cells, and these are the nanoshells, and it is going and specifically binding only to the cancer cells, and when we apply the infrared light, okay, it is destroying only the cancer cells and the healthy cells are intact. So these nanoshells of size 120 nanometer in width, okay, and which is having a glass as a core and followed by gold as a shell, and we can also tune the size of the shells to absorb light and heat up at various wavelength. And when you add these shells to these cancer cells, and when you apply the light, and it will kill the cancer cells in the particular location. So let us see how we can use albumin nanoparticles for delivery of anti-cancer drugs. So we can make the albumin nanoparticles with the size of 100 to 250 nanometer, and here the active drug in nanoparticle is in non-crystalline form, amorphous. Okay. So it is readily bioavailable state, and mostly we can load the hydrophobic drugs into the hydrophobic packets of these albumin nanoparticles. Example is paclitaxel and curcumin. Okay. And here the concentration dependent dissociation into individual drug bound albumin nanoparticles could be possible, and we can control the drug release by simple cross linking reaction. So it can slowly release the drug. So the presence of functional charged groups including amino and carboxylic groups offer albumin with various possibilities for surface modification. So these albumin nanoparticles having surface groups like amino groups or carboxyl groups. So that will be useful for various surface functionalization. We can also add antibody or peptides, and we can specifically target this nanoparticle for cancer cells. And around 7 albumin based drugs or imaging agents are in the market, and around 10 such products are under clinical trials for various applications including oncology and diabetes. So this is a list of albumin based nanoparticles and imaging agents available in the market, and some are under clinical trials. So let us see an example of Abraxane. So Abraxane is an example of NAB technology, that is nanoparticle albumin bound technology. So Abraxane is a solvent free nano version of Taxol. You can see the difference between Taxol and Abraxane. So here they are using anti-cancer drug paclitaxel. For dissolving 6 milligram paclitaxel, we have to use this much amount of organic compound, okay, which is toxic. In case of Abraxane, you can see here we are dissolving 100 milligram of paclitaxel in 900 milligram of albumin, and here we are not using any surfactants or solvents, okay. So that is the advantage of this Abraxane, and this Abraxane received FDA approval for metastatic breast cancer. And you can see the difference between the Taxol and Abraxane. Here the paclitaxel is only 6 milligram, and here we are having 100 milligram, okay. So that is why these protein based nanoparticles have wide applications in anti-cancer therapy. So it is a biocompatible nanocarrier which will have a lot of functional groups, okay. So it is easy to functionalize, and also we can easily target for cancer therapy. So let us see another polymer, that is dendrimer. This is an artificial polymer, okay. So the word dendrimer comes from the Greek word dendron, meaning tree, and meros means part. So it is having like a tree like structure, so that is why it is called as dendrimer. And the advantage of dendrimer is we can load anti-cancer drug in several locations. For example, in the cavity we can have the encapsulated drug, and on the surface we can have the adsorbed drug, so the drug can be adsorbed on the surface, and we can also add the cleavable linker, and we can conjugate the drug here. So we can attach the drug to this dendrimer in a different ways, okay. So that is the advantage of using this dendrimer for anti-cancer therapy. And we can also make multifunctional dendrimer based nanocarrier, which will be having therapeutic agent, also it will be having a imaging agent. So we can easily monitor the drug delivery efficiency. So in this example you can see here the dendrimer was used, and the anti-cancer drug is epirubicin. So the epirubicin is one of the very good anti-cancer drug, and it also has intrinsic red color fluorescence, and on the top of that we can also add carbon dots, so that will give a green color fluorescence, okay. So we can easily monitor the delivery of this drug, as well as we can also monitor the nanoparticles uptake by the cancer cells. So we can use it for intracellular imaging, and also we can use it for studying the cellular death, okay. So how this anti-cancer is inducing the apoptosis in the cancer cells. So the next example is we can also use the nanofiber for anti-cancer therapy. So these nanofibers can be produced by electrospinning, so which I will explain in detail in the next lecture. So using the electrospinning we can make the nanofibers, and these nanofibers can be loaded with anti-cancer drug, okay. And this is a electrospinning setup, and here you can see here this is a core shell nanofibers. That means inside the core we can load one kind of anti-cancer drug, and the shell we can load different kind of anti-cancer drug. So the core shell nanofiber is like this, okay. So we can make a nanofiber like this, and inside we can load anti-cancer drug 1, and in the shell we can load another anti-cancer drug, okay. So the advantage of having two anti-cancer drugs here, like each will be having a different kind of pathway to attack the cancer cells, so it will synergize the cancer therapeutic efficiency. So in this example we have used 5-fluorouracil, okay. So that is in the core of your nanofiber, and curcumin is in the shell of the nanofiber. So using these two different kind of drugs, it will enhance the anti-cancer therapy. The final product of your nanofiber will be look like this. This is the anti-cancer drug loaded nanofibers, okay. And again you can see here the core shell fibers can be tuned to release the drug. So if you are cross linking the core, we can control the drug release also, okay. So, by tuning the cross linking we can control the drug release also, and this core shell nanofibers provide a controlled and sustained release of anti-cancer drugs for preventing local tumor reoccurrence after surgery. That means, so the main drawback of your tumor surgery is once you remove the tumor, again the cells will grow again. Okay. So, to avoid that, after the removal of tumor we can place this kind of anti-cancer drug loaded nanofibers at the surgery site. So, that will slowly release the anti-cancer drug and it will prevent the reoccurrence of cancer cells. So, let us see what is theranostic nanoparticle. Okay. The theranostic nanoparticle means it is a combination of therapy and diagnostics. So, that is called as theranostic nanoparticle. Instead of doing diagnosis separately and therapy separately, so we can combine the therapy as well as diagnosis in a single nanoparticle, that is called as theranostic nanoparticles. So, these are called as multifunctional nanoparticle or theranostic nanoparticle. So, this is a typical example of your multifunctional nanoparticle. Here you can see here we can load two different kind of anti-cancer drug A and drug B, and we can also have contrast enhancer. Okay. So, that is like your imaging agent, we can monitor the drug delivery and also we can monitor the where the nanocarrier is going, and also cellular uptake, everything can be monitored. And we are having PEG, okay, that is polyethylene glycol, that will enhance your biocompatibility and also it will protect your nanoparticle from immune response. And we are having targeting moieties. Okay. So, this targeting moieties like antibodies which will go and specifically bind only to the cancer cells. Okay. And also we are having this permeation enhancer. So, once it bind to the cancer cell, so that will enhance the permeation of this nanoparticle to the cancer cell and it will enhance the release of anti-cancer drug. And the same multifunctional nanoparticle, instead of having polymeric core we can have the magnetic nanoparticle core. So, we can use it for various applications like bioimaging as well as drug delivery applications, and we can also use it for targeted drug delivery. So, we can inject the nanoparticles and we can use the external magnetic field, so that the magnetic nanoparticles can stay at the particular location for more time and it can release the drug slowly. So, here you can see here this is anti-cancer drug loaded ionoxide nanoparticles. So, when you inject it into the artery, so that will go to the tumor location, okay, and you can use that magnet and the nanoparticles can stay in the tumor location for more time and it can release the drug and it can be useful for targeted drug delivery and cancer therapy. So, let us see some of the barriers to this nanovectors delivery. Some of the barriers are like endothelial and epithelial barrier and reticuloendothelial system, enzymatic degradation and hemorrheology. So, these are several barriers to this nanovectors delivery. However, most of the barriers are already overcome by the recent advancement in this nanotechnology, but still some of the barriers has to be overcome, so that we can make this nanotechnology based therapy as a efficient therapy for cancer. I hope this nanotechnology will play a major role in protecting the patients from this dreadful disease. So, as a summary of this lecture, so in this lecture we have learned what is cancer and also some of the background of cancer treatments, and we have also learned what are the drawbacks of chemotherapy and advantages of nanotechnology, how this nanotechnology can overcome those drawbacks of chemotherapy, and also we have learned what is passive targeting and active targeting and what are the various nanomaterials available for cancer therapy, and we have also learned what is theranostic nanoparticle. Okay. So, I will end my lecture here. I thank you all for listening to this lecture. I will see you in another interesting lecture.